Okay, Physics 4.1, magnetism. So let's start with the look at the syllabus. It's not a very long unit, so let's just get it done. Um, so we start with the properties of magnets. So state the properties of magnets. So it's just a basic list of about four. Magnets attract ferromagnetic objects. So ferromagnetic means ferrous means iron, so it should be ferrous objects. We'll get to that one a little bit later. The magnetic field at the poles of a magnet is greater than at the middle. So the field at the poles is stronger than the field in the middle. The big rule, like poles repel while opposites attract. That's the big rule of magnetism. And those poles are north secant pole and south secant pole. And that's based on the Earth's magnetic poles. Hold up, where's my pen? Oh, there we go. And that's based on the Earth's magnetic poles. Hey, this isn't. There we go. All right. So the second objective is give an account of induced magnetism. So magnetic induction occurs when you take a magnet and you put it near a magnetic magnetic object, and it effectively turns that object into a magnet. So it gives it a north secant pole and a south secant pole. So in this situation, we place these nails in the magnetic field of this magnet. So once induction starts to happen, the opposites will attract, and that's why it's sticking together. So this nail develops two poles. So let's look at induction in this piece of iron right here. As I stroke the iron with a magnet, the south end is attracting the north. So it pulls all the norths this way. And as a result, this piece of metal develops two poles, a north pole and a south pole. Now the south would be the opposite of the north. All right? So if we were to place a magnet underneath some iron filings, we've all seen this experiment before. When you do that, use a piece of plastic or plastic bag. It creates this odd pattern, and this pattern, when sketched out, shows us the magnetic field lines. Now, magnetic field lines, like it said in the properties of magnets, it's stronger on the poles than in the middle. And a weird little fact about magnetic field lines, what they do, in order to demonstrate the strength of the field line, we would draw the field lines, I am very bad at this, closer together or farther apart. So if the field lines are very close together, then the magnetic field is very strong. If the field lines are very far apart, then the magnetic field is very weak. So of course in this area, the field is very strong, and in this area, the field is very weak because those lines are so spaced out. Okay, now a simple experiment to demonstrate magnetic field lines is we place these little plotting compasses on paper, and we just connect the arrow tips to the next one's butt, and you'll notice, let's see if I can do this, that it will create that shape that you saw in the previous slide. And if we do this multiple times, we will get the typical field line shape that you see there. All right, so magnetic domains theory. In a magnetic substance, so let's take iron for example, all the atoms are arranged and they're scattered, well not scattered, but each atom has a mini north side and a mini south side, okay, and they're all facing different directions. Now when I start to do magnetic induction, or if I run electricity through it, what happens is all these little north and south sides, which we call domains, they all start to straighten up, and all the norths go to one side, and all the souths point the other way, and as a result, there is an overall north and south side. So that's what magnetic domains are about. Now, there are ways to make these guys go back to scattered or all over the place. One is to put alternating current through it, which makes the electrons run that way. then run that way, then run that way, then run that. So it makes all the norths and souths get mixed up. Another one is to just bang it a bunch of times. And the last one is to heat it. As you know, heat causes the molecules to move faster, and they'll bump and collide and turn and twist and blah, blah, blah. So if you want to demagnetize a magnet, you could bang it, you can stick it in an outlet, or you can heat it up. Okay, so we're going to talk about soft versus hard magnets and permanent versus temporary magnets. So if I take a piece of iron and I put a magnet near it, just like certain friends that you have, they only act a certain way when you're around, right? So iron, when a magnet is near it, will turn into a magnet. And then as soon as the magnet goes away, it starts to act like regular iron again. Alright, so let's go through it one more time. Iron, you put a magnet near iron, it starts to act like a magnet. So it has a north side and a south side. You move that magnet away, and it acts like iron again. It's just a piece of metal. Steel, on the other hand, if you put a magnet near steel, it'll act like a magnet. And then if you move the magnet away, it continues to act like a magnet. So we give these two different terms. For steel, we'll call steel a hard magnet or a permanent magnet. I don't know how to spell permanent. I'm sticking with that, permanent. And then for iron, iron is a soft magnet or a temporary magnet. Okay, now these have two very different uses. For an iron magnet, we make electromagnets out of those guys. So think about that machine that picks up cars at the dump. Because that's made out of iron, as soon as I turn the current off, it'll drop the car. If that was made out of steel, when I turn the current off, the car would stay stuck to it, which would kind of make it useless. Alright, now steel magnets, this is what we make other magnets out of, so it's hard. So horseshoe magnet, your typical, did I put a picture? Nope. Your typical magnet that you see on cartoons, Acme. Man, I'm bad at this. There's your horseshoe magnet. So that's made out of steel. Speaker magnets and permanent magnets. Okay, so let's take a peek at this curriculum. Did we state the properties of magnets? Yes, and you have a list. Give an account of induced magnetism. What happens when you induce magnetism? Done. Distinguish between ferrous and non-ferrous. It's not a really big thing. Ferrous means contains iron. Non-ferrous means does not contain iron. Please note there are a few non-iron magnetic substances like cobalt and nickel. And I think liquid oxygen and some form of graphite as well. But just stick with cobalt and nickel because I have no idea what I'm talking about. Describe methods of magnetization and demagnetization. You can magnetize by stroking that piece of metal. You could demagnetize by kicking it across the room. Describe an experiment to identify the pattern. That's with the little mini compasses. Distinguish between magnetic of iron and steel. Done. Different uses. Done. Okay, now let's see if I can actually find the stupid switch to stop the recording because I lost it. Oh, hello.